All right, finally. That was almost 10 minutes. Okay, we are in the process of finding extrema, absolute global, max mins, when we don't have a closed interval and or when the EVT does not apply. So we were looking at this function here. First thing you want to do with the function is find its domain, okay? So we were saying we couldn't divide by 0 or take the square root of a negative. We set up this inequality to solve, and we found out that positive numbers live strictly between the X-intercepts. So the domain of the function is from -2 to 2, okay? Now what do you get when you plug a 2 or a -2 in to F? You get 1 over 0, which means there's what there graphically? Vertical asymptotes, okay? So remember, we're trying to sketch a graph of the function F. The graph on the right of the parabola is not F. That's just the radicand. So there's -2. There's 2. There's a vertical asymptote here, and the graph does not live to the left. And there's a vertical asymptote here, and the graph does not live to the right. All right? So what else can we use then to help us sketch this guy? What are some other tools you've learned over the years? We haven't really done any calculus yet. How about X or Y intercepts, right? How do we find Y intercept? Yeah, you don't want to have to just plug in arbitrary values, but you could make a table of values, F of 1, F of 2, plot them and connect the dots, but judiciously we choose values like X and Y intercepts. So if you plug in a 0, which is in the domain, you're going to get 1 over the square root of 4, which is 1/2, okay? So that gives me a little bit of information. I'll just label that as 1/2. How would I find X-intercepts? Set it equal to 0. So if I set f of x equal to 0 being a fraction, it's going to be 0 when the what is 0? The numerator. Is the numerator ever 0? No. Not even that one time in college he went dressed as 0 on a dare. He was still a 1 on the inside, even though he looked like 0. So there's no X-intercepts. No solution to that. There's no X-intercepts. Now that is pretty revealing, right? Because now I know that it's not going to cross the X-axis, so it lives above. We're kind of limited in the things it can do, okay? What about symmetry? Symmetry is always good. Is this function even, odd, or neither? Remember the test is this. If you replace x with -x, if you get the same thing you started with, it's even and has y-axis symmetry. If you get the opposite of what you started with, it's an odd function and it has origin symmetry. Yeah, this one's an even function. There's only one variable and it's being squared, so plugging in negative or positives will be the same. All right, so we're kind of limited then in what it could do. It could possibly do this. It could possibly look like a parabola. That's supposed to be symmetric on either side. It's not really. And if that were the case, the absolute minimum would be 1/2, right? But is there another option without crossing the x-axis? Sure, it could actually do something like this. And you can actually have still symmetry, and now you have points that are lower than 1/2 that are still above the x-axis, right? How can I, without a calculator, how can I determine using calculus whether it's the parabola-looking thing or the W-looking thing? Very good. Set f prime equal to 0, because the number of critical values that I would get would help me determine what it looks like. Do you agree? All right, so let's go ahead and find the derivative. It's time to bust out the good stuff, bust out the calculus. So I'm going to rewrite this function. I'm going to bring everything to the top and say it's to the -1/2 power. 4 minus x squared to the -1/2, just so we can use the chain rule, right? And the 1 in the top gets absorbed. Okay, so here we go. F prime of x is -1/2 blob to the what power? -1 gives us -3/2. And then I write the blob in there, 4 minus x squared, times the chain rule. The derivative of 4 minus x squared is parentheses -2x. And then if I clean that up, we got a 1/2 and a 2 that divide out. We get a negative times a negative, which is a positive. So we're just left with two factors, a factor of x, and then the other factor that's negative exponent goes back in the bottom, back under the square root, 4 minus x squared cubed. All right, so now if I set it equal to 0, that's going to equal 0 when the what's 0? When the numerator is equal to 0. So that's the only horizontal tangent that I have. But could there be other critical values from the denominator? It is a square root, right? What do you get when you plug in a 2 or a negative 2 into that? Yeah, you still get 2 over 0 or something over 0. So would those be critical values since they make the derivative undefined? If I plug in a 2 or a negative 2, would they be critical values since they make the derivative undefined? They are not in the domain. So vertical asymptotes are very, very important, but they're not critical. Okay, they're not critical values because they're not in the domain. But what that means then is as we approach 2 or negative 2, not only are the y values going to infinity, but the slopes are going to infinity as well, or negative infinity. So now that I only have one critical value, at x equals 0, I can pretty much get rid of the option of a w, or it didn't even have to be a w. It could have been kind of really wiggly. It could have done something like that, right? But every time it would have done that and gotten lower, it would have had more critical values. So there it is. That should be what the graph looks like. And so we can now answer the question, right? F has a min, an absolute min of y equals 1/2 at x equals 0. It's also a local min, yes? But it's also the absolute min. Does it have a max, an absolute max? No. So we'll say and no max value. How about that? Cool. So that was just sketching the graph. Didn't take a whole lot of effort, really. Domain, 1 point, the existence of no X-intercepts, and a little bit of calculus. Okay? Questions on 10a? All right. 10b. Go ahead and sketch that one on your own. That's a piecewise function. Those are pretty recognizable pieces. So this is one that you should be able to sketch really quickly. And then you can talk about max and min. Piecewise functions, they're the exception to every rule. They can be designed to be kind of almost counterintuitive. Before I sketch it, I want to do something kind of just, you might already have the result, but just a review question here. Let's test for continuity, okay, with the correct notation. So remember that would be the limit as x goes to 1 from the left of f. Then we'd have f of 1, and then we'd have the limit as x goes to 1 from the right of f. Road, bridge, road. The left of is the top one. It's the less than, so I plug in and I get 3. F of 1 is also the top one. That's where the equal sign is. That's 3. And the right of is the bottom one. That's greater than. You plug in and you get 3. So here would be your argument, right? Since, I'm not going to write since. It's really supposed to be because 3 equals 3 equals 3, comma, F is what? Continuous at x equals 1. Does that mean it's also differentiable then? No. Let's test for differentiability now, but not using the alternate form. So for that, we'll need a piecewise derivative, and that's going to be a negative 4x when x is less than 1. We don't put equals there because we're trying to see if the derivative does in fact exist at 1. And then the bottom is going to be 1 when x is greater than 1. So with the correct notation, the limit as x goes to 1 from the left down with f prime, you plug in your 1, you get negative 4. And the limit as x goes to 1 from the right of f prime, we get 1. And so notice we don't have to find f prime of 1 because that's what we're trying to decide if it exists. Does f prime of 1 even exist? No. So because negative 4 does not equal 1, comma, f is not differentiable at x equals 1. In other words, x equals 1 is not in the domain of the derivative. F prime is undefined at 1. It only lives to the left and right. Okay, so that's kind of a cool review. But to sketch it, because we're looking for max or mins, the most interesting value of x is 1. And if we hadn't done it already, we would want to know the y values where one ends up and the other one starts. So by direct substitution, we came up with 3. And we put a solid dot there. So now to the left of 1, it's going to look like 5 minus 2x squared. That's a parabola that opens downward, right? And so the y-intercept should be 5. So it's going to look something like this. We'll call that 5, I guess. And then symmetrically, it's going to do that. And it'll keep going. So there's 5. And then to the right of 1, it's the line x plus 2. So if we hadn't done it already, we would figure out where it starts. It starts at 3, and the slope is 1. So now, stop. Now it's going to go off like this. There we go. So there's the graph. Now it says to find the absolute max or min over the domain. What is the domain of this function? Yeah, it is all real numbers. And we could have decided that in the beginning. I said it's the first thing you should do, but we have 2 polynomial pieces, and notice it's explicitly defined to the left of 1, to the right of 1, and at 1. So it's got all the x values covered. All right, so now let's look at this graph. Do we have any extrema, that is absolute or global extrema? We have 2. Absolute extrema. Is there an absolute maximum value over its domain? No, that arrow up here means it goes up forever and ever and ever. Do we have an absolute or min, a global min, a min? No, this arrow means go down forever. So this one has no extrema. Now it does seem kind of weird to say no extrema, right? Because then you're like, well, what about at 0 and 1? So maybe we'll say, okay, clarification, although it's not needed. There's no global extrema or no absolute extrema. It doesn't hurt to put that in there. But do we have any local extrema? Yes, okay. So F has a ... local max of what? Y equals 5 at x equals 0. Yep. And a local min, it has a local min also of y equals 3, at x equals 1. What's the value of the derivative at 0? 0. What's the value of the derivative at 1? D and E. Those are critical values, right? Relative extrema only occur at critical values on the open interval. So, yeah, both those are critical values. So EVT is nice. When does EVT work? The closed interval argument? What's the if part of the EVT? Continuous on a closed interval. Good. That's the same condition for the IVT. You don't even have to worry about the graph. You can just trust the theorem. But if it doesn't apply, you're going to have to try and answer it some other way using all of the skills that we've learned over the years. Graphing could be very, very helpful. All right, any comments or questions on example 10? All right, there's one more to go here. Sometimes we need our calculator's number crunching ability to solve equations by finding X-intercepts for us. All right, so there's three things that College Board expects you to do with your calculator. Find numeric derivatives, which we've been doing, right, Math 8. Later on, finding numeric integrals, which will be Math 9. And then the other one is solving equations, okay? There's two ways to solve equations. You could set one in y1, one in y2, and see where they intersect, or the way we're going to do it here. Using your calculator's equation solving ability and not just its max-min ability, find the extrema of this function on the interval from -1 to 1. Okay? So what I mean by not its max-min ability, if you sketch this in y1, let's say you have a hill or a valley, your calculator, if you hit second trace number 4, has a min-max feature. You could like block off the graph here, and it'll scan that area and give you the high point. That's not even doing calculus to find calculus information. So rest assured, I or College Board will not give you a calculator question where that's even an option to do that, okay? So if we're trying to find the absolute extrema, where can they occur? At one of two places, either endpoints, which we have -1 to 1, and at critical values. Does the EVT apply to this function on this interval? Yeah, that's a continuous function, and we have a closed interval. So we are guaranteed both a max and min. So let's go ahead and find the critical values. We're going to need the derivative. Notice I haven't even picked up my calculator yet. F of x equals, what rule do we use on the first one? Product, okay? Unless you want to factor an x out of both first. I'll just do it, product rule. So that's 1 times e to the -x plus x times, for some reason this is an easy one to miss. What's the derivative of e to the -x? Negative e to the -x. Yeah, I've seen a lot of students just say it's e to the -x. For some reason, when it's just the -x, they forget the chain rule. If that had been like e to the 5x, most people remember the 5. But when it's just a -1, they forget the negative. All right, so there is the first term, and then the derivative of 2x is 2. So let's clean that up just a smidgen. That's going to be e to the -x minus x e to the -x minus 2. Now, is that ever undefined? We always consider it first. Is that function ever undefined? No, it's defined everywhere, right? Because it's a combination of exponentials and a constant. So f prime is never undefined. So the only critical values we're looking for then are where it's equal to 0. Now, how would we go about algebraically solving something like that? Not even. We can't even, right? So this is where we go to the calculator. Now, anytime you're solving an equation, just purely an equation, it's not like a context of a graph and something intersecting it, you should try to remember to get everything on one side and set it equal to 0. So if you set two functions equal to each other and you're trying to solve it, I would recommend getting everything on one side and setting it equal to 0. Especially when you have variables on both sides. The reason being is if you graph a variable in y1 and a variable in y2, you're looking for their point of intersection. They may intersect at some crazy y value that you can't see. So you might be fishing with your window to find it. But if you set everything equal to 0, do we know where 0 is? Y equals 0? That's the x-axis. So that's the easier way to do it. So if you have a calculator, you can play along. If not, I'll just show you the keystrokes here. It's not going to be terribly difficult. Remember, this is one of the big three things. Everyone, we just had a calculator on the desk, right? Oh, well. Watch and learn. There might be time to grab one as slow as this thing. Okay. Just have to threaten it. Okay, so here we go. E to the -x. E is second ln to the -x. Click to the right. Boom. Minus x times another e to the x. Second ln to the -x. And then we've got a minus 2. Now, you don't want to hit zoom 6. Your calculator can find x-intercepts for you. I'll show you how. What window should we be in for our x's? Yeah, remember we said the values have to be in the domain first, and then they have to be in the interval. Normally we find them algebraically, and then we have to check to see if they're in the interval. But if we're finding them graphically, you could just set your window, x min to -1 and your x max to +1. Okay, that way you're not tempted by outside critical values. Oh boy. Now for your y min, y max, okay, we're trying to find x-intercepts, right? Here's what I would recommend. Instead of -10 to 10, which is probably default, go ahead and stretch it out to something small like -3 to 3, but still keep it symmetrical, because that's going to keep your x-axis right in the middle. And now you hit graph, and boom. Okay? So you can tell there's a critical value. Now your calculator can find it by going second trace number 2. It's going to ask you for a left bound. So you can scroll. Oh, man, look, you got to scroll to the left, and then you got to scroll to the right. Hang on, bear with me. Oh, bother. Okay, so there it is. And then you click to the right. And then you can say right bound. Yeah, and so it'll scan for a 0 in between there. You get -0.37. Did you see how long it took me to scan? I'm not going to do that. Here's how I want you to do it. If you have it set equal to 0, instead of using your calculator's built-in root function, just sketch 0 in Y2. Now when I graph it, I see the x-axis. Now we do second trace, not number 2, but number 5. And look how much easier it is. There's only 2 graphs on there. There's only 1 point of intersection. Enter, enter, enter. Boom, we get the same answer. So what's faster? Enter, 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 or scroll, scroll some more, scroll, okay, enter, and then scroll, enter. Yeah, I think the answer is obvious. Enter, enter, enter is obvious. So we write down the answer and we go to lunch. -0.374. -0.374 or -0.375. Now that's just the critical value. Ay, caramba. All right, we're going to have to use that after lunch. So here's what I would recommend. Go to lunch, and we'll talk about it afterwards.